Today we are joined by Daniel Berardi. To make Wi-Fi networks ready for post-quantum era.
Uh, there are some studies on the IEEE, I think, and another companies. If we break the SSL, if we break TLS or another encryption protocol, there is a problem all over the globe.
Now let us talk about WPA3.
One of that is PMF. PMF is protection management frames. The main goal of PMF is protect from management, which says, hey, disconnect these people, reset the connection. This is a way to protect the open networks.
Yeah, then we also have offline dictionary attack. Can you talk a little bit about that?
This handshake of WPA2, and we can use known dictionaries and derive the phrase with these dictionaries on offline, so we have enough time for proof.
What were the early security mechanisms developed to address this problem?
Well, one of the first security mechanisms is turn off your router. No, I'm kidding.
Do you think standards should look into mechanisms where control frames are also protected?
I think it's in this scenario at this day, it's not a good idea, because the control frames are used to be lightweight and used to be fast.
Hello everyone, welcome to Weekly Wi-Fi Wisdom podcast series where we talk everything about Wi-Fi and the tech that surrounds it. I'm your host Sainath. I'm WLAN QA engineer at Candela Technologies, and today we are joined by Daniel Berardi, and he comes with over a decade of experience in networking. And in today's episode, we are going to look at Wi-Fi securities. Daniel currently works at Telecom Argentina, and he is currently working as NOC analyst. I'd like to thank Daniel for gracefully accepting our invite and joining us in this podcast to share his insights on Wi-Fi securities. I'm looking forward to learn about Wi-Fi securities from you, Daniel. And that's about it about Weekly Wi-Fi Wisdom. And I'd like you to introduce a bit about yourself and what you do currently, and then we can get into the topic.
Okay, thank you, Sainat. Nice to meet you. Nice to be there. So I'm glad you invite me and you read my articles, and I'm very happy with that. So currently I work, as you say, at Telecom Argentina with like a network analyst. I work in this time with fiber optics and all the transmission protocols on the network of the Argentine. So this is a huge topic too. And my interest on wireless began when I started to learn for CCNA. I started to practice and read this documentation. I need to understand from the transmissions of the wireless networks, which is amazing. And after that, need to learn more, goes to wireless security, which is an interesting topic. It's amazing for to talk about it. So nice to see you and nice to be here.
Right. Yes. Let's get started. So let's start with understanding about the perspective of Wi-Fi security, right? So during the early days when Wi-Fi was introduced, so what's the perspective back then to get security into wireless networks?
One of the first things of having security on wireless networks was protect the data from anybody which is seeing us on the network. The main problem was in wired networks, we have cables from one endpoint to a switch to a router. So this is the data traveling protected. And in wireless networks, this is a problem because we use as a cable the air and so anybody can see this data flowing through the air and read this. Even when we don't see, we can read this with wireless access point with wireless cards. So anybody can read this data we are sending. We don't want that. We want to keep privacy on our networks. We want to anybody can see our keys or passphrase or anybody we are sending. So this is the first warning on the wireless networks. To solve that, we need to improve and create a security wireless.
Right. So the context is clear. We need to have security in place so that an attacker who is in proximity of wireless network cannot intercept what is going on in the network. So, what were the early security mechanisms developed to address this problem?
Well, one of the first security mechanism is turn off your router. No, I'm kidding. So one of the first security mechanisms we use is the UAP. The UAP in early days, it was the first security protocol for wireless networks. And the name is very reveal is wired equivalent privacy. So we need a wireless network equivalent like a wired network. So this first protocol is used to encrypt the data. Has used to have an authentication, but not a real authentication. The main goal is encrypt this data. Is send data encrypted from one point to another, and if anybody reads, they can understand that. So the WAP was very weak in when we say when it starts, and after that also is weak. So we need to improve this protocol. This protocol is based on an encryption algorithm called RC4. RC4 was one of the first encryption algorithms for wireless networks. It's not created for that, but it's used on that. But one of the problems of RC4 is has some bias, and when we found some problems on the key algorithm of the RC4, which reveals our passphrase if we capture enough data. So this is one of the principal problems of WAP, but has two another problems, and the security is very dangerous in this time. So the second problem or the WAP was the organization vector is used to encrypt the data using RC4. So we have one initialization vector, the key or the passphrase used on the WAP, and with these two elements, we create a key stream. A key stream, it's a stream of keys. It's very easy, but we create these key streams, and with these key streams, we can encrypt the data using an XOR operation. So when we create that, we have an encrypt payload and send to another people. What is the problem? One of the second problems of the WAP was the IB was very tiny. It's 24 bits. In 1997, when it was released with the WAP, 24 bits is good enough. They think it's good enough, but it's 16 millions of possibilities of IB. So if we repeat, we have the passphrase is fixed, we create that. The RC4 algorithm use the passphrase and the IB. If the IB repeats, we create the same key string again. We start to crypt the data one another time the same way. So if we send the same packet, like an IRP packet, we send a lot of IRP packets every time. So if we send one another time the one IRP packet with the same key stream, we obtain this. We obtain the same. So if an attacker knows the structure of the payload of an IRP packet, they can guess what is the key stream. So this allows the attacker not to obtain the passphrase, but they can read the data over the with the same ID and create packets, valid packets to send the access point. So the access point is reading valid packet if is an IRP spoofing or DNS spoofing or something like that. We can send anything. So this is the two main problems on the WAP, which really are really hard.
Right. So one is no authentication in the first place, and the other one is reuse of initialization vector over time when there are multiple packets. I mean, more packets in the network.
Exactly.
Yeah. So the second problem was using the same initialization vector if there are more number of packets over time. So initialization vector is being repeated. So what mechanisms were developed to address this issue of initialization vector reuse in WAP?
Okay, well, to to improve WAP, we create WPA use to keep. Was a patch was not a real solution. When they create, they need to fix WAP fast, but they don't have time, and of course, maybe it's for money or sometimes. But the hardware of used on WAP doesn't support a better improvement. So they need to use a patch, a software patch to use the same hardware for use it to WAP to WPA. WPA improve with to keep the security. One of the first things they do is increase the IB from 24 to 48 bits. This is a huge increase for these days. Not unbreakable, but it's not unrepeatable, but it's good enough. Some another thing they use is put some authentication. They create the four-way handshake and start to use it, and they also create a MIC. It's a integrity check. WP has a integrity check, but it's not integrity check. It's a CRC checks the transmission of if the transmission fails, the CRC fails. So this to keep install MIC, but need to remain the CRC of WAP because it's a hardware thing, so they need to use that. Also, they create this mic when they create this mic and improve the IB and they are much better, but they still using RC4, this bias or this problem which it creates, which permits to cover the entire passphrase. So this is a fix, but it's not good enough. So when we finish with that with WAP, when they create this, they know they need a new improvement. They don't have they don't can still doing that with WAP because they doesn't works. They one of the attacks which breaks the keep at the end was called an attack called Big Tews. This is the last name of the investigators which create this attack. So this attack used the problem of the CRC, this check transmission, to they use this and use an attack called Chop Chop. This is a funny name. But the main goal of this attack is cut the last byte, recalculate the packet, send to the access point, and because the CRC is not secure enough, also it's not an integrity check, it's only a transmission check. The access point read this data, and we can guess which is the byte we got. So when we recalculate, we can send 256 times until we can guess which is the byte we are coding. So following this procedure, we can cut all the packet and obtain the key stream. If we obtain the key stream, we can create packets, malicious packets, and send to the access point, and the access point accept that and use. So the MIC, even the integrity check of the keep itself, it's also weak because they don't have enough power on the chipset to make a MIC good.
Right. So web and TKIP are fundamentally weak because they use RC4 algorithm. So how did AES improve the situation with WPA2 when it was introduced?
It's a new paradigm. It's a new way to see the security network, the security wireless. So we use the good things of WPA, which is the handshake, the four-way handshake, and we use AAS replacing RC4. So this is AAS is an encryption algorithm based on blocks. It's a cipher algorithm based on blocks. We can cipher blocks of, in this case, 128 bits. So we can improve the security using IAS because first, they don't have bias like RC4. At least until now, they don't have bias. So this security, this encryption is very helpful because these blocks are encrypted each one with IAS. If works with CCMP. CCMP, it's the boss of AAS. They send CCMP send a packet, cut a packet into chunks of 128 bits, and send to IAS. Say, okay, give me a key stream. IAS gives a key stream to CCMP. CCMP encrypts the data with this, and one of the things that are much better than in AAS is the use of IB is eradicated, and we use nonce created by CCMP. We send these nonce. They say the CCMP send some key features, not repetitive, which improve the efficiency of IAS. So we encrypt this packet, these chunks of 128 bits, and after that, CCMP has another tool, has another type of algorithm, which also creates MIC based on IAS too. So the packet enters on CCMP. CCMP asks for IAS for a key stream, encrypts the packet, and after encrypt the packet, the CCMP sends these chunks and encrypts on IIS to obtain a MIC, a 64-bit MIC. This is very, very secure. It's good enough for modern networks. So this is essentially WPA2. Also has another improvement, but this is the main goal of WPA2 is improve this engine and obtain a real encrypted payload. But another thing with the WPA2 insert on the networks, on the real networks, is the enterprise grade of the networks to obtain security without a passphrase using user and password authentications with radius servers or with TACAC server even. So this is a huge improvement on the networks.
Yeah, so RC4 has a problem where the key stream can be repeated if the initialization vector is repeated over time, right? So that problem, is it completely solved in AES, or can that also be happening in AES, CCMP?
No, NAS it's solved completely because AS use a key PT key pairwise transition key. It's a temporary key for each session, so we can repeat these IB collisions in the new networks of WPA2. We use a nonce, which is more powerful, more big than the IB. So this creation, and also AES doesn't create, it works a little harder because they use more power, more compute power, and it's very hard to obtain these key streams based on the data obtained.
Yeah, so the A nonce, the nonces used in AES also adds for additional security. But despite that, WPA2 is known for its vulnerabilities also, right? So attacks like offline dictionary attack and crack attacks are exploited WPA2. So can you talk a little bit about those attacks and what made WPA2 vulnerable to them?
Yes, how I say before, the WPA2 remains with the good things of the WPA, but it's not good enough. The WPA, the four-way handshake was a problem for the WPA2. AS is robust, CCMP is robust, it's still used at these days, but the four-way handshake in this moment in WPA2 was weak. The process of the four-way handshake is it's quite easy. The access point sends announce to the client a derivate passphrase to his PSHare key, PM key, Paraguay master key. This Paraguay master key was created and send it doesn't send this create a mic, and this mic is sent to the and I is nonce. This is a supplicant nonce. The access point create a nonce are the same, not the same numbers, but it's the same type of information. The access point send the announce to the client. The client creates the MIC, derive the PT key, and creates the SNONs. They send the SNONs and the MIC to the access point, and if the access point it's all okay, check the MIC, the SNONs create send it for the PT key, and install each and the access point install the PT key. When the client receive this order to install the PTG, the client sends okay on an SK, ASIC to the access point. If we capture this confirmation from the client to the access point sends again the order to install the PTG. Which is the problem on here? When we are reinstalling the key, when the client they are installing the key, they start to send data. They don't want they send only the confirmation to the access point and start to send data. Normally, the DHCP request on another packet. So if we capture this access point sends again the order to install the packet. The protection of the encryption comes from the nonce, this number created by the client or by the access point and used by CCMP to create the key stream of AAS. So if we, when the client sends the first packet, sends with a nonce of one. So if we force to the client to reinstall the PD key, the client again send the packet with the same nonce. So we have two packets with the same key stream. Always, that's the same problem before. If we have two packets with the same key, we are in troubles because we can read this data and create packets to send it to the access point and create valid malicious packets to send to the access point and create RP spoofing, DNS spoofing, and things like that. That is the crack attack or key reinstallation attack. So this is one of the most common attacks on this WPA2.
Yeah, then we also have offline dictionary attack.
Okay.
Yeah, can you talk a little bit about that?
Yes. The other problem with that, we can capture handshake of this handshake of WPA2, and we can use known dictionaries and derive the passphrase with these dictionaries on offline. So we have enough time for prove every key we want. I remember some years ago, like 10 years ago, one of the biggest ISP on Argentina used the as a passphrase the identification number and 014 if you are a woman or 004 if you are a man. So if you create a dictionary with only that, which is it's very easy, you can break any network from this ISP. So this has a very huge problem for this enterprise, and the people doesn't change the factory false passwords. They use the encryption of they use which the ISP sends. So after that, they need to improve this this passphrase.
Right. So now let us talk about WPA3. So what mechanisms in WPA3 were introduced to tackle attacks like crack and offline dictionary attacks?
Okay, one of the things of WB3, it's a huge topic and it's very, it's very chamative for me. It's a very amazing for me because they use mathematics and they use all the things I learned on WPA2, on WAP, what to do, not to do. So they start first creating a protection over the forward handshake. They create a side SIA dance so that they can dragonfly. This is a process to create a password element without using the partial key. They use only the passphrase, my password 1234, to create a password element from a mathematical perspective. The process is very similar to the four-way handshake, but first the access point and the client needs to create this password element. An algorithm called it's a ecliptic curve from Galois. They use this ecliptic curve of Diffie-Hellman. To imagine that is a curve created with a mathematical formula. A square equals x cube plus ix plus b, I think, if I remember good. This curve, it's encapsulated in a finite field, and the thing it's I there are two ways to obtain this PWE, is power element, but one of the ways is deprecated because of one attack after the WP3 is released. So the main idea is obtain points over the curve to create this password element. They use this curve and pass through some mechanism. So with this equation, they increase the one counter, a counter, and send the data to the curve. If the point belongs to the curve, this is the PWE, the password element. If the point doesn't belong, increase the counter and try again. What is the problem with that? This hunt and peck problem is somebody find if you are sending data and trying these values, you can guess the point measuring the time which the access point responds to the packet. So after that, they use hash to element. Hash to element, it's nearly the same, but we don't use this process one another time. We only use a function which every time gives you a point inside this curve. We create this password element, and with this password element, we send a side commit with a scalar and an element from the access point to the client and from the client to the access point. So both check the security of one of the other, and if all is okay, they send a sign confirm. And this password element is used to create the PTK, the PM key of for one handshake. So this improves the security much more. Of course, this even is more computationally expensive. So also
Okay.
we need problems with that, but it's improving the security much more. The UPA tree also include some mechanisms for protection. One of that is PMF. PMF is protection management frames. These are included on WPA2, but it's not mandatory. We can use or don't use. The main goal of PMF is protect the frames from management, which says hey, disconnect these people, reset the connection, and this management between the client and the access point, which is a problem if it's not protected, because anybody can, in one of the attacks is the crack attack, you disengage the client and force to make the reinstallation attack, make the forward handshake one another time. So protecting these frames, we avoid to the clients be disconnected because an attacker can are forcing them. So this is improvement. And another thing is OWE, opportunistic wireless encryption. So this is a way to protect the open networks, the networks on the airports, on the coffee shops. This encrypts the information of these wireless connections without a passphrase. They don't use a passphrase, but it's protected, but with this algorithm. This is are the most known features of the WP3.
So yeah, as you mentioned, PMF was introduced to protect management frames, right? So do you think standards should look into mechanisms where control frames are also protected, or added some integrity checks, because attackers may exploit control frames sometimes, and maybe sending an RTS frame to one of the member in the network and then expecting a CTS. So it's a wastage of air time, right? So any mechanisms in consideration to protect control frames?
I think in this scenario, this day, this is not a good idea, because the control frames are used to be lightweight and used to be fast to maintain, and is maintain the spectrum free from another talkers, so we can avoid collisions on the spectrum, and putting some security layer and encryption layer over these frames can be very bad for the network environment, for the network quality. I think this is in this scenario in these days with this technology of these days, it's not good enough. It's not worth it to add these layers.
So we all are seeing about the future. So many say that quantum computing will be the future. So where we have huge processing improvements, right? I think in one of the interviews, the Google CEO has also quoted that quantum computing will break encryption as we know it today. So are standard bodies taking any steps to make Wi-Fi networks ready for post-quantum era?
There are some studies on the IEEE, I think, and other companies, but at this time they don't have any standard created, because they don't know what happened with the post-quantum era. We doesn't know with what's the real problems of the post-quantum era. We think the quantum computers can process the information very fast and very good, and break these encryptions, which I don't know, break IAS encryption. So this is a very huge problem for the security, not only for wireless security. Wireless security is one of them, but if we break the SSL, if we break TLS or another encryption protocols, there is a problem on all over the
Right.
globe. So the IEEE are creating some algorithms based on post quantum algorithms. They have, I think, two ways to do that. I think they are doing from using the same encryption protocols used today, and added a layer to post-quantum era or post-quantum algorithms. And another phase is extend these protocols, which we have to include these post-quantum algorithms to include inside the algorithms created today. So, but it's nothing is right on stone. We have very very big problems with the idea of quantum computer. Even we have very big problems with artificial intelligence on these days. So I think we need to work in that fast.
Right. So this is about practical advice. So what if somebody who are working in Wi-Fi security and enforcing security policies, what practical advice would you give the engineers who are deploying security policies?
Okay, I think one of the learned things on the studying the wireless networks, it's nothing is truly secure, nothing is invulnerable. We need to create networks secure. Of course, we cannot use open authentication at these days, but we need to know if the security can be breaked anytime, any day, and the protocols we think are really, really strong, the state of the art of the algorithms or whatever really are really vulnerable. So they need to create security thinking on that. I think one of the better approach is the zero trust approach is for me a good way to start to design any security on these days. And the other approach is read, state update, and at the end we need to create networks which are safely, which can fail safely. So if the the problem exists, the algorithm breaks, the any problem which we have, we need to create a network we can solve that and start to work and maintain these things working, even if the security is a risk.
Right. So yeah, I think we have covered all the list of questions that we have. So if you have anything that you'd like to address to our audience on this topic, you can please address our audience.
Okay. One of the things is be great with sign up to invite me, and I think the wireless security is really important on the day to day because the wireless device are more and more each day, any day. Practice, keep updated, and create network securities with wireless security with a good assumption of the work of the wireless security. So thank you, Senad, for inviting me. Thank you for the time to express myself, and see you.
Yeah. Thank you, Daniel. Thank you for joining our podcast series and sharing your insights on Wi-Fi security. Um, yeah. So for the audience, if you enjoy the episode, please leave a like, share, and subscribe. And please stay tuned for our podcast series for upcoming episodes. And if you have any questions for Daniel, please leave them in the comments so that I can take them to Daniel and get them addressed. Thank you so much. We'll meet you in the next one. Thank you for your time. Thank you for watching.